Welcome, deep divers, to a special Science Corner deep dive. Today, we're tackling one of those really intriguing questions in artificial intelligence. How do these incredibly powerful transformer models, the ones behind ChatGPT and all that advanced translation, how do they actually think? It often feels like a bit of a black box, doesn't it?
Oh, absolutely. You see these amazing results, right? But understanding the computational process underneath, the real how it gets there, that's been a major challenge.
Oh, yeah.
It's not like the older neural networks, RNNs, recurrent neural networks. They had a more, let's say, sequential logic. You could almost map them to traditional programming steps, transformers. They work very differently.
Yeah.
And that's really made it hard to, grasp the internal workings.
Yeah, it's like you've got this amazing chef, but you can't see the recipe or how they're mixing things. So today, our mission is to, peel back some of those layers. We're going to introduce you to a really interesting concept, a computational model, and actually a programming language, too, called RASP. That's RASP, the Restricted Access Sequence Processing Language.
What's that?
Think of it like a blueprint, maybe, a way to actually peek inside the mind of a transformer.
That's a good way to put it. RASP is designed to give us this high-level view, an abstraction. It lets us try to think like a transformer by translating all that complex neural network stuff, the weights and activations, into more symbolic, understandable programs. It's about seeing the logical steps.
That's a really key distinction then. So we're not trying to perfectly copy the neural net itself, but understand the logic it might be following.
There.
What kinds of steps or operations does RASP actually use to model this? How does it work?
Well, at its heart, RASP is actually a pretty simple language. It's just carefully designed to capture the, let's say, the unique information flow constraints you find in a transformer when it's processing a sequence of input.
Okay.
The goal is really a clear, interpretable model. It helps us understand how a transformer processes information, but at a more abstract level. So it focuses on sequence operations, not the really complex dance of individual neurons and weights.
So it's thinking in terms of words or maybe positions in a sentence and how they relate, rather than just raw numbers crunching away.
Precisely. Conceptually, a RASP computation works with sequences of information. You can think of them as lists, maybe lists of words or numbers representing their positions in the sequence. Importantly, these sequences always have a fixed length, just like how a transformer usually looks at a defined window of text.
Okay, that makes sense for the setup. But every language needs verbs, actions, right? What are the fundamental operations RASP uses to, think like a transformer?
Right. There are basically two main kinds of operations in RASP. First off, you've got element-wise operations.
Okay.
These are simple. Think parallel computations applied independently to each item in a sequence. So imagine you have a list of numbers, like 1, 2, 3, and you want to square each one.
Right, so 1, 4, 9.
Exactly. Each number gets squared on its own, no interaction with the others. This is quite similar to the feed-forward parts, the sublayers, inside a transformer, where each input token's representation gets processed individually before moving on.
So if you had two sequences, say S1 as 1, 2, 3, and S2 equals 4, 5, 6, adding them element-wise would just give you 5, 7, 9.
Precisely. Each position is handled separately.
Okay, that seems clear enough. That covers the sort of independent processing. But where does the real transformer magic come in? The way it connects information across the whole sequence. That's the powerful part, isn't it?
Absolutely. And that's where the second and, much more powerful type of operation comes in. Select-and-aggregate.
Select-and-aggregate.
This is really the core of RASP, and it directly models the attention mechanism, the thing that makes transformers so effective. So first, there's the select operation.
Okay.
This takes two sequences. You can think of them as keys and queries and some kind of comparison, like are they equal or is one less than the other? The output is something we call a selection matrix.
A selection matrix?
Yeah.
What does that actually look like? What does it do?
Think of it like a map or maybe a spotlight controller.
Yeah.
For every position in the output sequence you want to create, this matrix tells you which positions in the input sequence it should attend to or gather information from.
Oh, yeah.
It's essentially deciding for each word or data point, okay, which other words in the sentence are most relevant for me right now? And this directly translates to those attention matrices you often see visualized for transformers. You know, those heat maps showing which words pay attention to which other word?
Got it. So select is like the transformer figuring out who should I listen to in the input. And then once it knows who to listen to, how does it actually, use that information?
That's the aggregate step. Once you have that selection matrix, That map, the aggregate operation, takes a sequence of values, maybe the original words or some representation of them, and uses the matrix to combine them. Often it's by averaging the values from the selected positions into a new sequence.
Okay.
This is a direct parallel to that final weighted averaging step in a transformer's attention mechanism. It's where the information from all the relevant input tokens gets blended together to create a new, richer representation for each output position.
Could you maybe walk us through a quick example? Something simple that uses both select and aggregate, like, I don't know, reversing a sequence of words.
Yeah, sure. Reversing is a good simple case. Let's say you want to reverse apple, banana, cherry. Using RASP, you'd first define a select operation. For the first output position, it selects the last input position. For the second output position, it selects the second to last input at banana, and so on. It essentially creates a selection matrix that flips the indices.
Okay, so it maps position 1 to 3, 2 to 2, 3 to 1.
Exactly. Once that selection matrix is built, the aggregate operation then just takes the original words, apple, banana, cherry, and uses the matrix to pull the values according to that map. The result, cherry, banana, apple.
Ah, I see. Simple task, but it shows how select picks the sources and aggregate puts them together. Clever.
It reveals that fundamental selection and reordering power, yeah.
And you mentioned there's another key RASP operation too, something called selector width.
Yes, selector width. This one's quite powerful for certain tasks. What it does is, for each output position, it computes the number of input values that a particular select operation chose for it.
The number. So it
Yeah.
counts how many things were selected.
Exactly. A simple way to think about it is with a selector that finds, say, same tokens in a sequence. Imagine the input hello. If you apply selector width to a same token selector, well, H appears 1, so its count is 1. H appears once, count is 1. The first L, it selects both L's, so its count would reflect that maybe. Actually, let's refine that, a better example. If a selector just points from each position to all identical tokens, selector width on hello would compute a histogram like 1, 1, 2, 2, 1. Because H appears once, E once, but each L sees 2 L's total, and O appears once.
Okay, so it's basically counting occurrences based on what the selector finds, like building a frequency count or a histogram.
Precisely. It's effectively counting how many times each query attends to matching tokens based on the selector's logic.
All right, so we have these building blocks, element-wise for parallel stuff, select and aggregate for the attention-like interaction, and selector width for counting based on selections. How does putting these together help us program and, more importantly, understand more complex things transformers do?
Okay, let's take a more complex task, one that really shows off RASP's power. The double-histograms problem. This isn't just some abstract puzzle. It's a fantastic way to see how multi-layer transformers might work.
Double histograms. Sounds tricky. What's the goal there?
The task is, for each token in your input sequence, you need to count how many other unique tokens have the exact same frequency as itself.
Whoa, okay. Can you give an example? My head's spinning a bit already.
Sure. Imagine the input is, say, PCDef. Let's break it down. The A appears 3 times, B appears twice, C appears twice, and D, E, F each appear 1.
Right. 3 A's, 2 B's, 2 C's, 1 each of D, E, F, and the section's just a start token.
Yeah, like a beginning of sequence token.
Okay.
So the output should be section 111222333. Let's see why. A has a frequency of 3. Is any other unique token type present 3 times?
No.
So A maps to 1.
Okay.
Now B, it has frequency 2. Is there another unique token with frequency 2? Yes, C. So there are 2 unique token types, B and C, with frequency 2. So B maps to 2. Same logic applies to C.
Got it. B and C both map to 2 because there are 2 types with that frequency.
Exactly. And D, F all have frequency 1. How many unique token types have frequency 1? 3, D, E, F. So they each map to 3.
Okay, that makes sense now. It's a multi-step counting process. How does RASP handle that?
The RASP program is actually quite elegant. It first uses select to find all tokens identical to the current one. Then, just like our simple histogram example, selector width computes that initial frequency count for every token.
So step 1 gives you the frequency of each token.
Right. But the key is, it then uses another layer of select and selector width. The second layer doesn't look at the tokens themselves. It looks at the frequencies calculated in the first layer. It uses select to group tokens that have the same frequency, and then selector width counts how many unique tokens fall into each frequency group.
So it's like a histogram of the histogram counts.
That's a great way to think about it. And what's really fascinating here, and this is, I think, a core finding of the research, is that this RASP program for double histograms, it compiles directly into a specific transformer architecture. 2 layers, 2 attention heads.
Wow, so RASP isn't just describing it, it's predicting the kind of transformer needed.
Precisely. This is where RASP becomes predictive, not just descriptive. The researchers actually trained a standard transformer on this exact double histograms task. And guess what? It learned attention patterns that were incredibly similar to the ones the RASP program implicitly defines. If you look at figure 1 in the paper, you can see the visual comparison side by side. It's striking.
That's amazing. It's like looking under the hood and seeing the blueprint actually matches the engine's structure. Strong evidence that RASP is capturing something real about how transformers compute.
It really is. It moves RASP from just a neat idea to a tool with real explanatory and predictive power for actual transformer behavior.
So beyond these perhaps slightly niche counting tasks, can RASP also help describe solutions for more complex, maybe more symbolic reasoning problems, things people thought were harder for transformers?
Yes, absolutely. RASP has been shown to express solutions for things like recognizing Dyke languages. These are sequences of balanced parentheses, but maybe with multiple kinds, like needing to balance with and with B independently.
Right, like checking code syntax or complex grammatical structures.
Exactly. Or even more complex variants like shuffle Dyke 2, that's where you have balanced pairs, but they can be interleaved. Like before RASP, getting transformers to solve these often required very specialized hand-designed architectures. RASP provides a much simpler, high-level way to describe the necessary computation.
And does it also predict architectures for those?
It does. For example, the RASP program for Shuffle Dyke 2 is pretty concise, and it compiles down to a 2-layer, 3-head transformer. And importantly, this matches existing manual constructions that people had figured out through trial and error. So again, RASP seems to capture the essence.
So RASP isn't just for simple sequence fiddling. It can get quite abstract. Which brings us, I think, to the big so what. Why should you, our listener, really care about this RASP language? What are the main takeaways for understanding transformers better?
Well, I think one of the biggest implications is RASP's ability to predict the maximum number of layers and attention heads a transformer seems to need to solve a given task.
The maximum needed. Or the minimum.
Ah, good clarification. It predicts an architecture that is sufficient. Let's say it predicts the complexity required by the RASP program itself. The research suggests this prediction often corresponds to the minimum effective complexity needed in practice, but it's perhaps safer to think of it as predicting a sufficient complexity. This is huge for understanding and designing efficient transformers in the real world. Think about optimizing those giant language models. Knowing the likely complexity needed for certain capabilities is incredibly valuable.
Yeah, that could save enormous amounts of computation and energy if you could avoid overbuilding the models. What did the experiments actually show when they tested these predictions?
The experiments, they're summarized nicely in Table 1 in the paper. They wrote RASP programs for various tasks: reversing sequences, histograms, double histograms, sorting, those Dyck languages we mentioned. And consistently, the architectures predicted by RASP, like 2 layers, 1 head for reverse, 1 layer, 1 or 2 heads for histograms, 2 layers, 2 heads for double histograms, 2 layers, 1 head for sort. These predicted models achieved really high accuracy, often 99.5% or better, when actual transformers were trained with those specs.
Okay, so the RASP predicted architectures work really well.
It strongly suggests that RASP provides a pretty good upper bound, or maybe a tight bound, on the necessary architectural complexity.
So how tight is that bound? Did they try training transformers that were smaller than what RASP predicted, like fewer layers or heads?
They did exactly that, yeah. And this is where you get some really interesting results, some surprises even. They detail this in Table 2. For most of the tasks, if they reduced the number of layers or heads below what the RASP program suggested, the transformer's accuracy just plummeted, often down to chance levels, basically failing completely.
So for most tasks, the RASP prediction seems pretty close to a minimum requirement.
It really seems that way. It indicates the predictions are, remarkably tight in many cases.
But I think I heard there was an interesting exception, something about the sort task.
That's the one, yes. So RASP predicted that sorting a general sequence would likely need 2 layers. However, when they trained 1-layer transformers on the specific sorting task they used in the experiments, some of them actually performed surprisingly well.
So RASP was wrong there. Or maybe just overly pessimistic.
Well, it wasn't exactly wrong about the general case, but the transformer found a kind of shortcut. The researchers dug into how the one-layer model was succeeding. It turned out it wasn't really implementing the general RASP sorting logic. Instead, it cleverly exploited the fact that the input alphabet, the set of possible characters or tokens, was bounded and relatively small.
Meaning there weren't that many different things it needed to sort.
Exactly, and because of that, it could effectively implement a much simpler algorithm, basically a bucket sort. It could assign each possible input character to a specific bucket or range and then just order the buckets. It didn't need the complex comparisons across the whole sequence that the two-layer RASP program assumed for a general sort.
Ah, okay. So it found a different, more optimized solution tailored to the specific constraints of the experiment.
Precisely. Which is a fascinating insight in itself, right? It shows that while RSP tells us one way a transformer can solve a problem, a real trained transformer might find alternative, sometimes more efficient paths, especially if it can exploit specific properties of the data, like a small alphabet size.
That's really cool. It shows the transformer isn't just blindly following a program, it's finding solutions within its capabilities.
Yeah.
Okay, so beyond predicting architecture size and revealing these kinds of shortcuts, how else does RASP help us understand other common design choices or phenomena we see with transformers?
It sheds light on quite a few things. For instance, think about restricted attention transformers. These are models where, for efficiency, you deliberately limit which parts of the input each token can attend to.
Right, like maybe only looking at nearby words.
Exactly. RASP helps us reason about the fundamental trade-offs there. If a task, like general sorting, requires a certain computational complexity, maybe something like O(n) log n operations, which needs fairly global comparisons, RASP can show that restricting attention too much, making it impossible to achieve that complexity, means you genuinely lose expressive power. You can't solve certain problems anymore.
So RASP helps quantify the cost of making attention more efficient.
In a way, yes. It helps define what capabilities might be lost. It also gives insights into things like sandwich transformers. That's where people experiment with the order of the sublayers, the attention layer, and the feed-forward layer.
Oh yeah, I've heard putting the feed-forward layer first or second can make a difference.
Empirically, it does, and RASP helps explain why. If you put the feed-forward network too early, before the aggregate step, the attention mixing, it doesn't add that much computational power. Why? Because each token is just processing its own information independently. It can't really generate fundamentally new insights without combining information from other tokens first.
Right.
But if you put the attention layer, select-and-aggregate early, it efficiently gathers information from across the sequence. Then the subsequent feed-forward layers have richer, context-aware information to process. RASP clarifies this interplay between gathering information, aggregate, and processing it locally, element-wise feed-forward.
That makes intuitive sense. What about those special tokens, like the section in your example, or the BOS CLS tokens we often see added to the input? They always seem necessary, but why?
RASP offers a perspective here, too. These special tokens, like a beginning of sequence BOS token, often provide a fixed, sort of neutral reference point in the sequence. RASP programs suggest this can be really useful for things like condition counting. For example, implementing selector width, our histogram counter, might actually require fewer attention heads if a BOS token is present, because computations can use that fixed point as a stable anchor to aggregate counts across the sequence, rather than needing more complex relative comparisons.
Huh. So it acts like a computational anchor point.
It can simplify certain computations, yeah. It's often a subtle but potentially important role.
It really sounds like RASP is acting as this powerful Rosetta Stone, helping translate what's happening inside the transformer's black box into something we can actually read and reason about, almost like a program. And you mentioned earlier, it seems like real transformers can actually learn to implement these RASP-like solutions. It's not just a theoretical analogy.
No, the research provides strong evidence for this feasibility. They did experiments using something called attention supervision. This means that during training, the transformer wasn't just rewarded for getting the final answer right, it was also nudged to produce attention patterns similar to the ones predicted by the corresponding RASP program.
So guiding its internal strategy.
Exactly. And when they did this, the transformers achieved very high task accuracy, and their internal attention maps looked remarkably similar to the idealized RASP patterns. You can see this alignment in several figures in the paper. Figures 1, 4, 6, 7 all show examples of this. It really seems to close the loop, showing that transformers can learn to compute in ways that are well described by these RASP programs.
That's a truly significant step, then, in demystifying these incredibly complex AI systems. So, just to recap for everyone listening, RASP gives us this powerful high-level lens. It lets us understand and even predict the behavior of transformer encoders in a way we couldn't before. It's like a bridge between symbolic programming, which we understand well, and this often opaque world of deep neural networks.
Right. It lets us reason about the underlying computation with a clarity that just wasn't there for transformers before. It definitely moves us closer to really understanding how they manage to do what they do, at least for certain types of structured tasks.
And as we wrap up this deep dive, it does leave us with a rather provocative thought, doesn't it? Well, RASP is fantastic for helping us think like a transformer for these kinds of well-defined, maybe even programmable tasks. It also highlights that some of the most impressive AI feats, like truly open-ended creative language generation or deeply nuanced machine translation, well, these aren't easily captured by a RASP program, or perhaps by any traditional programming language we currently have.
That's a crucial point. It raises this really fundamental question. Does RASP help define the limits of what a transformer can understand and compute in a structured, interpretable way? Or does it mainly define the limits of how we, using our current symbolic tools, can understand it? Are there modes of computation happening in these massive models that RASP or maybe even programming itself just isn't equipped to describe yet?
A really fascinating question to ponder. Does RASP show us the edge of the transformer's mind, or the edge of our current understanding? Something to definitely mull over. Thank you for diving deep with us today on Science Corner.